Okay, people, I'll give you my pretty good suggestion of where I think it started, and that will be here. This material here, as identified in another part of this the report. This is the part, let me do a circle. This is the section that buckled. All right, this section here would be here. This is the section that buckled, fractured first. Now remember, it's dynamic. As this is happening, it just didn't go, okay, I'll just finish off and crumple this in this direction. Now, once that starts buckling, it can no longer maintain the force on the other side. It's not countered. You know, it's not pressure equal everywhere on the out exterior. Now, it starts, this pressure over here, it's not being stopped by any pressure over here because of that. It's buckled in. This pressure out here, let's say it's 6,000 psi, shoves this in. This whole section here gets shoved this direction. Doing so, we get the outer layers, like 4 and 5. Here, let me back up an image. So we get our 4 and 5. It slides inwards because of the outer pressure. And layer 4 and 5 is near the top. Or it's the top layers. But they get sheared off the face of the interface ring. They get sheared off, so layers 4 and 5 get sheared off the interface ring, which is here. They go inbound, and the front nose cone is still under pressure from the outside, trying to close in on the hull all the time to try to buckle this area here. All right, and then the rear is doing the same thing. It's trying to buckle the same area. That means it's trying to crush in and crush in. But the carbon fiber being a solid tube, if you will, outer tube, you know, solid material, of course composed of layers, can resist the buckling, the pressure that's being applied, the inward pressure. Now, I did mess with a couple of engineers I know and say, tell me what the reduction is with the 6,000 psi surface tension pressing down on it and pushing up on it. How much of a reduction do we get that? I think we get an angle, you know, if this could finally, if you could release, if I had the ability to snap and release these two from each other, just snap the center away. If I could just click my fingers and disappear, these two would just come flying into each other and impact each other. I don't have that ability, but what happens is when that part buckles, it now can say, oh, I see an imbalance now. Remember, the pressure's all there. It says, oh, you used to have resistance here to stop me, but now it's not there. So that creates the ring wanting to torque in right at that location where it's buckled. The ring pressure on it wants to torque it in, and it rotates. So the back of the head here rotates. Here's the dome with the eyepiece in it. It rotates this way. So looking at from the top view down, it's clockwise. It rotates clockwise, and we see this is on an angle into the dome. The force to still drive it laterally inside. All right, that's why we don't see this buckled here, crushed away. This rotation, keep track of this rotation here. This is very important. Pulls it off the interface ring over here. Now I'll show you that. So let's do the. Hold on, Bruce. Bruce. There you go, Max. Hold on, guys. Let me make sure Max eats. Go ahead, Max. Go ahead. Bruce is giving Max a hard time. Good boy. I'm going to send you packing, Bruce. So anyway, good boy, Mac. Yeah, thanks for the shout out. All right, so I'll prove that to you in just a minute. But I want you first to get the concept that if all the forces are pushing on this, trying to close it in, we're looking at the top view. All right, there's the eyeball. It's trying to push it into the buckle and buckle this section here. All right, but it can't. Not until it actually buckles. This buckles upon buckling there, this piece here. This just can't drive straight in still. Let me give you a new position. It does this. And it still drives in. How can I prove it does that? Right here is where it was connected in the interface ring. Remember, there's an interface ring with that. Let's say that's the carbon fiber edge right here. And the dome It's like the interface ring works around it, and then a dome goes on it. They were connected at one time together. It pulls away from that. Well, how does it pull away? It has to shear it also. So it shears and rotates it off. There's an interface ring right here. So it wants to rotate along with the dome. Now let me get you that rotation. And that rotation looks like, sorry, I thought I went the wrong direction. I thought I was going the right direction. I didn't have to edit that part of the video. Right here. So here we're looking at, well, the report says 90% of the epoxy at the top, which they call the zero position. He also calls it the upper position, I think, and top, the person there. This is epoxy mapping, if you will. So here's the top, and this is the epoxy on the ring down here. He says about 90 degrees of epoxy there. But I want to bring your attention up here. This is where the interface ring would have sat, would have seated right there. Interface ring would have seated on this. And you don't see it seated anymore. So it didn't just go directly in. So here's the end cap with the interface ring. And upon this buckle here, that one I showed you, this just didn't go straight in. All right, it didn't do that because it's no longer here. It didn't buckle it, didn't fracture there. So it rotated off of there first, with that being our starting point, the buckling point. So here's my model I made up for you. That goes there. All right. Also have the other pieces here, samples. So when we get our, this is the shell, if you will, the part where the humans were located. So when you get to this buckling here, the two ends immediately start going in. But watch my hand. My hand's going to double as a dome now. It just doesn't push down, right? It doesn't buckle this because we don't see it buckled. We don't see it buckle. In fact, when this buckles here, this shears off, tucks in behind the dome, behind the interface ring, and it gets shoved forward, shoving into the, so it buckles, the other side comes in, gets pushed down, and goes back into outside of the interface ring, pushes it out and comes out to the outside of the interface ring back here. And this is what I just said, where it tucks. Here's the interface ring, layers 4 and 5. They shear off the other side of here. They shear off, tuck under, as I said, and they come into here. They come into and push into the back of the dome. The dome's already been impacted this time by the bottles and pushed it away, because we don't see this compressive moment here where it actually buckled it. Here is the bottle in the background. So it participated. This would be the floor section. The floor section, I don't think the bottles took a trajectory up, but I leave it. Here's the bottom, and here's the bottles. I leave it open that they could have taken a trajectory up, and we're looking at it that way. I need to orient myself again with this dome, with the rear cap, the rear, cap. What I'm using it for help me orient are these tabs, the well tabs. I've got a couple of them. They have a couple of them. So let's go back to the scale again, my model. So now I want you to, after that buckles, I want you to visualize my hand is the interface ring and that. If I just push back, well then all I do is buckle that. I don't get that tucking under. So this part of the interface ring, with it that I just showed you, it does this. It rotates because this is buckled over here. All right, once it buckles over there, the pressure out here is 1,000,000 pounds, but it's not equal anymore. See by my thumb here, it's not equal here anymore. Over here, though, it's now got a gap, if you will, a gap in the cylinder that protects, that stops this from buckling. That pressure here says, oh, I see the differential, and it rotates. Pivots like that, pulling itself off the interface of the carbon fiber. So here it is here. The pressure here is able to buckle, so off it comes. And now it starts driving in. It just comes off. Maybe it takes off the first or second layer. Maybe it grabs hold of that, but not number 5. Remember, this crushes in at the within this buckles, this comes in at the same time. The pressure of this is able to load with a torque action rotating and coming in. So much pressure is built up in here that it explodes outward. Now, water is not compressible, they'll tell you. Well, I compress hydraulics all the time to make it do work, such as using on excavators, rebar pull-out test, things like that. You're using the pump and you're creating this higher PSI to do the work. And your higher PSI translates to more work. So it's a lot of force behind that hydraulics. And this should be the cylinder, if you think of it. The pressure, the cylinder behind it, pushing it. But it's also pushing here. This is not for free. This is pushing. That end is also pushing this way too, to not as great a degree as this end, because this end pulled off. That slipped in. Pressure was able to get in there, and that bottle was able to be crumpled. Let's get to it. I'll say crumpled, buckled. So here's your layer 4 and 5. Like I said, they tucked under. Remember, there's 5 layers, all right? 5 layers. That's 5, and this is number 4. So 5 and 4 tucked underneath the interface ring. Tucked under to be able to come out there. But noteworthy, again, is it didn't shear right here. Forces weren't still driving at that point. The game's over at this point. It's fizzled out because it would have sheared, unless they show it. This would have sheared the section and beyond the ring. We would see it something like that, perhaps. Depending on how it hit, I mean, we could have that shearing inside still. I mean, this could be here, and then part of that could be like that, inside, internal. Meaning this part is crushed up inside. But we don't see that. Now, the part tying into the outer part here, this is all buckling. All right. There's a carbon fiber. This is the part that I said that came off, rotated, however you like to think of it, rotating the direction I showed you, and pulling itself off of there. And that's why this isn't buckled here, and why the other end is also not buckled, why it's sheared off, because again, the pressure is changed, pressure differential. And here is the the epoxy. We can see it slid, we pushed it off. We pushed it off. So again, I think the failure is on this side, as opposed to what you're looking at from here. I don't know the orientation, how much of a spin it took. I do believe it took a spin per the release of the curlicue, I call it, right, off the ends of this. They did take a rotation during this failure. Okay, so we have the top there, and then this one is interesting. What do I get from? How do I get there from here with that? That one's intriguing to me. That's the top piece, but that's the part that would have broken and rotated. This is the part top. Considering this is the top here, and considering this is the top back here, this would have went this direction. It would have been connected to the ring up top, and this where the cameras would have been connected across the interface ring. Why is it buckled down there like that? And it's not creating much of a the impact. The impact, could it have buckled it? But what blew it away from there? I think they will have better once they release the detail on how this is still interacting there. I would argue that it was somehow connected to the carbon fiber. When the carbon fiber pulled in, it pulled in and went down to inside this, past the interface ring. This little buckle here, as my man likes to say, sigmoidal. This buckle here would be impacting here. We might be able to determine that by looking closely at trading materials, glues and things like that. Everything comes in impact, trades materials, two things trading materials. There's your O2 bottle, right? It's also on the other side of the interface ring. And the interface ring, the interface ring we're looking at, this is a starboard right here. Here's this guy. That's the part that's connected to the carbon fiber. So now we're looking at the opposing side of this. This is where I think the collapse, the original failure started back here. So I'm looking at top view of this. Let's just do one side where I said it's collapse. It's like this. This is our collapse section. Let's put the other side in. And then let's put the dome on, the interface ring on. All right, interface ring and the domes and caps. So when that goes, the pressure differential happens differently. This rotates to the right. This shears the void here. The pocket in here is air, right? It wants to close it up. And there's all types of pressure all the way around here. So it says, I can handle it now. So it shears it off of the glue part I showed you up here in a different angle in the background. It shears it off of there. Push it in at the same time. This bottle. It's the bottle's very interesting. The bottle gets compressed. It gets ran back there, and the bottle did buckle. I mean, look on the outside of it. There's a buckle there now. Could it be an implosive buckling? No, I've seen the implosive buckling of bottles, and they look like this. This might be aluminum. It might behave differently. I don't know the rib structure of that. I would like to know, you know, the design of it. But it's like it's folded over the impact, so we're losing a lot of materials here. I do not think the carbon fiber had the ability to crush that tank. Let's say the tank was empty. It's aluminum. It's being impacted by the carbon fiber. Perhaps if it's, you know, really light aluminum and it blows out and it's empty at that point, but I'd probably get an implosive action at the same time. This is interesting. He says this is the bottom, so that would make this the bottom. And if I could lay this on the side, it means that this is the tab here, and this is the bottom there. So this piece here is the interface ring right here, and this is this. Okay, so there's that tab on the shell out there somewhere. This tab would be here. I'm going to clean it up now, which means that part we're looking at, if it is true, I'm sorry, let's get clarity on that. So if this is the bottom and this just went back to here, just fold it back over. There are two tabs, it turns out. There'll be another tab over here, and there'll be no rotation, and that means no rotation of the interface ring. Well, we need to orient it with this tab and this, these guys. And I can orient this, if this becomes the right side of the vessel, or let's see, looking from the front, where the door opens, this should be the, looking from the front, this should be the right side. How about that? So they're saying port or starboard. So looking at the eyeball, this should be the right side, and this should be the left side. All right, just so getting confused with port and starboard, like it's quite confusing with this vessel, because what are we talking about? Operating from inside, and he's sitting at the back. And I don't want to confuse you. I'll just give you orientation each time. So here's the eyeball. Here's the eyeball. The lens. And we have the window left and right. That would be in the back. Now in the rear, we would have this, which is this. Let me clean that up one more time. Eyeball. And at the back, though, no eyeball. So at the back, we're just looking at the interface ring, this bottom piece, which is here. This would be the right side, left side. So we're looking from the doorway. If we had to look it back and remove the carbon fiber and look straight back. And then at the bottom there, we would catch 1 and 2 hull penetrations. All right, and this would now say that and this is eliminating practically all the spin in this one. So now it buckles. Looking in the back at the tube now, it buckles on this side, the left side. So this side, the left side near the rear. Let's see top view. Oh, you know what? Back to camera. So leave this for a second. so we're buckling back here somewhere, not here, buckling here. So folding in, going in, that allows us to end cap to release from here and rotate in and drive. This will also, as it buckles in, this also gets driven down because of the pressure. This guy comes sliding across the rest of the carbon fiber, tearing apart layers, grabs the tank, shoves it in the back, breaks off the end cap, the interface ring back here. But remember, this is meeting it too, so don't forget that they're meeting. It's not just doing all the work. This is some meeting of the minds, if you will. So the meeting of the minds is the meeting of the ends. I want to show you something else. So I've already talked about the buckling of this guy, you know, kicking it out. It was rebound. It was probably bent out by the end, by part of this. And then the forces shockwaved a couple of times, and that's where we finally see our final location of all the materials. I want to show you the impact of this. This is pretty interesting now, looking at it from a different angle of the angle of incidence from this image. We're pretty deep. We're pretty deep now. All right, we're pretty deep in the sand over here. So that's not, you know, I don't know how much this thing weighs and how much that sand will displace upon impact. But now this gives me a little different idea. This is critical because the front side of this has that one little top connection that I love to see. If they didn't bring it up, they didn't show it brought up, and that's troublesome. This also is an interesting shot as you look at it now and really dive into it. I want you to note the rings, the full exposure there, but look, from here to here, it's not. So this ring snow plowed in. It came sliding into home base, right? It came, or diving into the angle of incidence that way, dove in, and this is where you get this exposure, but now all of a sudden we get this profile. A lot more sand around it. Internally, I think it's slid a bit because here we see a full ring almost. Back here we see sand built up on the back side of it. So I think this is our angle of incidence, the way it came in when it impacted. It slid for that little bit of time to snow plow this up to this part of this section of the one of the tabs, and up to the shackle there. This side's fully exposed, acting as a snow plow. The front dives in, the back starts dragging a bit. So here's might be the drag field in the back a little bit. It drags and it creates just this little bit of snow plowing effect. The shock wave of the sand and all that gives you the outer circumference of the sand area. This is that curlicue. It's stuck. It's embedded. I don't know if it goes there or it goes there, but there's the rest of that interface ring right there showing itself. And you can see sand is over top of it. It got buried. Now, could it have rolled and twisted and created this? I don't see any indicators of that. They don't show it to us. Besides that, I visualize a spiraling effect. Oh, he calls this forward, which is quite confusing because that's toward the aft. I don't know why he calls it forward. The wires should be noteworthy, how they were stranded here, how they broke loose of their connections. You can see this was just a so-so connection. This is a much deeper connection, frayed wires. And there's another wire there. I don't know where they belong to. Okay. But a closer image, you see now that there's the bottom of the ring here. And then there's just snow plow material. All this material here. Front fully exposed pretty much. And is buried here. So this is the way this came. That's the way it came to rest. So remember, you have that this is the front. And let's do this. It looks like that, right? You have that opening. And there's your lens, your lens. There's water pressure in here as this goes in towards the meet, you know, the back end coming this way. As they meet, there's a lot of pressure inside this compartment, this area here. That allows it to eject that out also without ever spit it out. You know, it's a plug, if you will. Poof, only designed to work one direction. Poof, it gets plugged out, it gets shot out. I don't know if it gets fractured out. You think they would be able to find some pieces? Apparently not. Did the bottle come to hit it? And then no, I think the bottle would go right through it then at that point. Right through the hole, right through the lens. So no. Or the window, they call it. This is what, part of the door, floor system, door system. It would tell you a story also because it looks to be no longer parallel. It looks to be bent. So they look like tabs that were like this. And this one looks bent, like it took an impact. Maybe chewed off some of that too. So you can find the materials where it made love to, where it traded its swap spit. Yeah, that's what I said. So inside here also, this dome, they'll be able to figure out what to trade it with it. And probably a lot of carbon fiber, which supports because there's no carbon fiber in that hull to begin with. So now all of a sudden you find carbon fiber traces on it. Then you know that, oh, it did slide in. All right, there's the, it looks like part of the gasket sticking up. And then let's move on. So we're looking at the data again. I now see this as like this, possibly the force coming that direction. And now I see it differently, rather coming at this angle of incidence, right? Now I see it kind of differently. Now I see it as, what if the angle of incidence is the other side? What if this this right here, and it came this direction? Now it's slammed into there, and now we get different burial and not just this. And that would help me why I don't see much snow plowing here from this direction. I would see more snow plowing, more of that piling of materials. What if this is the piling of materials? Would this also explain the debris field? And that, what if, because the debris field is very, very interesting here, how it's set up over here. So what if our implosion is somewhere, you know, like this section? The implosion happened, it takes a rotation during implosion, pins itself here, and they do their in the air there, they do their compressive moment. Sorry, did that one backwards. The dome, did it backwards again. The domes, what the hell? The domes do their trading off of pressure, going in and out. This one gets rotated out. There it is. There's the dome. So I see it kind of differently now. During that implosion and explosive moment, there's your materials over this side. If we look at it like that, like a little blood splatter thing, we get our residuals here on the outside. As this at such a great speed, it splinters and buckles and shatters this carbon fiber. Again, maybe over here, and then that rotation happens, and it sheds most of the material here, and as rotation happens, it flicks off its blood pattern, its carbon fiber splatter pattern, this direction. All right, and then here you are here. Okay, so I think I understand what he means by forward now. He's saying that's towards the dome. This is the lens. But this is your lens, and a forward direction. Maybe as simple as that. Now we move on. No, before we move on though, we take note of the position, and that's the curlicue. Like I said, I think it had a spin up for part of that to do that rotation like that. Although when they put it out of the water, it seemed like it had more turns on it, and we have more turns here also. So 1, 2, and 3. So I think that rotation with the dome attached to it, so the dome was attached to get this working, and the carbon fiber rotating at the same time spins it, rips it off. Gives us this can opener effect of the rim, the interface ring. So part of that, my theory of it rotating towards inbound would be this. It rotates inbound. Now this comes down, and I think we'll see it in an image over the other side. And the driving force of that would still be the, as far as these two meeting each other. Remember, they came close to meeting. It broke free at one point. It tore it free, and I think the dome might have clapped down pretty damn close to here. You know, it drug across this section here. It might have came down pretty close before, like a pool ball, elastically bounced off. Oh, and doing so, coming down, it gave this some nice little buckling effect. Buckling, what we observe. Let me see if I can find the other end of that. So there it is here again. This section. It goes inside. This is the starboard rail. Same thing. It's on the exterior of these rails. So I have the, I got the cap, the interface ring, and the cap to buckle that in. Because they're outside of the implosive area. They're not inside of it. I mean, the rebound could get it to throw some carbon fiber out, but that's not how this settled down. This settled down very interesting that it resolved itself pretty fast with the pressure equalizing. No one felt it at the top of the ship. This is, thousands of feet away. And it's like me saying I jumped into the damn ocean and you were 20 feet from me, you were 10 feet away from me, and you felt my shock wave next to you. Yeah, really? You know that you're not going to feel it. You don't even, you don't notice the person slapping next to you in an ocean wave. This was a burp. This was nothing, burp. This was nothing. It's like saying you heard a whale fart down there, or you just heard a shark get eaten by a great white, and I felt it happen, or a great white eating another great white. It's, no. That ship's displaced is too large, and if they just, with Captain or anybody saying they felt at the time they felt a shudder, yeah, that's just them wanting to put themselves into the picture there, or being deceptive. It's just not logical. Oh, incidentally, the Coast Guard guy said that I saw that last night when I looked at the Coast Guard, part of the Coast Guard's comment when they asked that question. He said, no one told it. At the time we came there, no one reported that they've heard that they correlated any explosion with any vibration on the ship. And now it comes out later that all of a sudden, yeah, I think I heard the fart down there. Yeah, sure. So this is the starboard rail right there. Slide up one. And this identifies the starboard rail. The rest of it here. So that rail also came inside the vessel. Inside the vessel. It was outside by the interface ring, and now all of a sudden it's inside. So this tells you that this what's going on there. Now that's just the end. This end only, not the other end. That's a different behavior. I showed you how that is. So this is the end, how you see it there, and hopefully this will be good enough for you. But this is the end, how you see it there. So once again, this, I'm taking a little liberty. I need to fracture this and make it bend in for you. But it bends in. At the same time, these both ends want to make love to each other, come in. But this one sees the pressure differential, and it's still, this one also sees it, obviously, and does a little rotation also, meeting at pulling away also. This one, same thing. They both orient towards each other, peeling off layers as they go. Some peeling off one end, pulling off layers opposed to the other. But this one comes off. That's why I showed you that lip. You can still see the interface ring where it would have been epoxied on, so it wasn't buckled. The whole piece is nice. So this shows you that this one rotated in, and part of the other end where it's damaged, some of it rotated in before finding a force that was equal to it, and then equal to this, a reverse counter force that was equal to it, and then it turned this direction. You know, it buckled back in. It kept the force driving this way, rather. It didn't really turn. It kept the forces going this way. This time it was able to buckle part of this end. Remember, this crushes in and out. So it pushes the back here. So there's a force now. It's got to drive part of this carbon fiber also. So it's like it's turned like that now, and it's coming in before it's come the rest. The interface ring gets knocked off. As we can see, it's in position. Again, buckles here, and this end does that, comes in. They do a pool ball thing, like a pool ball, elastic collision. This one goes off. I don't know what elevation they're at. This one goes there. This interface ring, remember I showed you, I don't know where it is in the debris field, but it comes off. It comes off. It's obviously turned. It's obviously turned flat. It snow plows into the surface, like that, comes to rest. So it's off the surface a little bit. All right, so that's the momentum on that. If we could figure out where this is, if it's over here, is it over here? Wherever this is, we can start figuring out how this ring relates to everything else too, especially with that direction. All right, so that means it didn't just fall from way up top. Way up at 3,000 feet, the elastic collision happens. I mean, the collision happens, the accident happens, 500, hundreds of feet up, meters. Eventually, this is what? Does it fall like that? Does it fall like this? That's a lot of meters, and we only get a little bit of sliding, a little bit of depth. I visualize it would be a much more impactful depth into the sand. The sand. And also it was on an angle, it was on an incline, an angle like that. So it would indicate that this was closer to the bottom upon implosion with this interface ring. Think about that, it was closer to the bottom because up high, we have a choice like this, or it breaks away and it goes like this, hundreds of feet away, 3 football fields away or 2 football fields away. I don't have it coming in an angle like that. All right, so what do you think? I think it's closer to the bottom. I also think that I just showed you how that works. Take care, guys. Love you. I'm going to end this video. George is banging in the background. He's telling me to take a pill and go to bed. I'll model some of the debris field for you on this. This is what this is about. And we'll put it into here. But I wanted to cut to the chase a bit and give you a cut to the chase, and then we'll do some background on it. But this is the way it's looking like. With that said, I do have some string and line to show you why the toe is wrong. I also understand they put a screw in it. I don't know if they put a screw in the carbon fiber and a plug. Craziness. Now, where did they put it would matter too. This thing broke up. I think it sheared between layers 3 and 4 during that loud bang they had. Now, part of the report, I finally got to read it tonight. It says that it cracked upon surfacing, but then we have the data that says, other data that says that it cracked below the surface, the loud bang. So you get multiple data points on that loud bang. One, it's at the surface after coming up, and the other one is below the surface. Nevertheless, I think between layers 3 and 4 is a failure. That we hear you see on dive 8 from dive 80 forward, where it's really making bullshit noises. The reason it's not the very inside. I think the weakness of this again is layers 3 and 4, and we can cycle loading. It said I had enough between 3 and 4. The pressure could not make it down distributedly equal down to layers 2 and 1, and so it made it down to layer 3, I believe. And then so this pressure kept doing layer 3, and they can get away with multiple dives still until it finally fails. Quite a few dives later, so the system did work. They just ignored it. They just ignored it. I guess, you know, he said it was give them a warning ahead of time, and it did. But the cost, which I would like to know, to replace this hull, swap it out with a new one, I'd like to know that. Don't get confused with version 1 vessel. I see a lot of comments. Version 1 vessel was Spencer Composites. Spencer Composites, hold on, George, did a full depth, 5 inches, I believe, and not multiple layers. Now, the other issue I have is the company that did there's 2 companies. He had one to make this, and I believe at that location, to make the 1-inch layer, they vacuumed it. And then he had to drive it, as I look at it on the map, over an hour, about an hour and 15 minutes. That's just direct drive, no traffic. An hour and 15 minutes on the road to get to the autoclave. So I imagine that was not very, unless they made some super beautiful, stable clamping system to transport it. I imagine transporting, even though you vacuum sealed, but you haven't set the epoxy, you have not set the epoxy. How do they transport it without some of the glue through vibration resettling inside that vacuum? I know it's a vacuum and it's supposed to be tight, but how tight was that vacuum? Could glue still settle inside of it? You know, like blood, like you vacuum pack meat and leave it out on the counter. The blood still settles. It settles, you know, it settles. So think of it as the blood, the epoxy, hour and a half, and you're vibrating it. So you're vibrating this epoxy and you're creating a weak point. Maybe that is layer 3 and 4 that was transported the same way every time in the same position at the 12. So they clamped it up at the 12 o'clock position, and happens that hour and a half creates the same weakness based on epoxy being segregated like concrete. Like you don't vibrate concrete too much or you'll segregate the stones and all. Well, maybe this got segregated through an hour and 15, hour and 20 minutes vibration or longer. You know, I don't know how long it took to get there, but they repeated it 5 times. So I don't think that was for free. I don't think that vibration going to the from one place to the next is for free. All right. Take care, guys. Love you. Oh, please give a shout out. Please comment. Thumbs up for the channel, please. Comment. That really helps out. Let's see what happens here. Comment about something about Titan, please. If you're going to comment, say the Titan words. Let's see if we can make the algorithm realize that we're talking about the Titan implosion, or you can type Ocean Gate or Ocean Gate, Titan, Titanic. That's probably reaching. Ocean Gate, Titan, Titanic, Rush, Stockton Rush. You'd have to say his full name then. Anything that would be identifier for that. Oh, anything you use for Google search. Please type it in there and then type your comment. I do read the comments, mostly all of them. Some of them I can't reply to because you might also put some things I agree with and then some not. Also, if you edit the comment, if I commented below your edit, I'm going to delete my comment because your edit looks like if you edit it and say, look, you know, you say one thing and then when you change it, you edit it, it looks like I'm agreeing to what you edited. And I do see the edits. It does come up on my side. The settings are set that if you edit, I'll see it. Most of the time, you know, Google's so. So I'll delete my comment unless your edit is grammar. So if you're going to edit, please just put edit to add, you know, grammar check or whatever it is. Just put it below the comment in the feed there, you know, edit to say I meant a, not an, or something like that, you know, grammatic repair or something. All right, hopefully that was helpful. Love you. Thank you. Please comment. Oh, share. If you get on Reddit or Facebook or whatever, share this. And I think I'm getting closer and closer with all this data here. You got a hell of a lot in this one. And all you people, tell me where you're from. Some of you I know are out around the world, so other than the United States. So give me a shout out, your location also. Take care. Thanks for all the shout out and love to the cats, the kitties, the strays I take care of.